When you hear the word Chernobyl, your mind probably jumps straight to the tragedy, right? The abandoned city of Pripyat, the human costs, it's all incredibly powerful. But there's this whole other story buried underneath all that, a story of incredible and, frankly, unexpected scientific discovery. So today, let's look at the surprising scientific legacy of Chernobyl.
So this is the day it all began. A safety test at the Chernobyl nuclear power plant goes horribly wrong. It triggers the single largest accidental release of radioactivity in history, and in doing so, it unintentionally created this massive, real-world laboratory for a field called radioecology, basically the study of how radiation moves through the world and what it does to the environment.
We're going to explore the 5 key areas where our scientific understanding just took this giant leap forward, all born directly from the fallout of the Chernobyl disaster. Almost immediately, scientists realized they were in completely uncharted territory. You see, all their existing knowledge came from studying fallout from atomic bomb tests. But that just didn't fit what they were seeing on the ground in Ukraine and Belarus. The contamination from Chernobyl was behaving in ways nobody expected. And this led them to the very first major puzzle, the radioactive material itself. It wasn't what they thought it would be. They started calling these things hot particles. And this is so crucial to understand. This wasn't just some radioactive dust floating around. Nope. These were microscopic fragments of the actual nuclear fuel from the reactor core, tiny, incredibly radioactive chunks of uranium oxide that got blasted into the atmosphere. Okay, in this slide, this really shows you the fundamental difference. Fallout from a bomb is mostly water-soluble. That means its radiation is immediately available. It gets into the ecosystem right away. But Chernobyl's hot particles, they were like these tiny, slow-release poison pills. The radiation was locked inside these little fuel fragments, and it would just leach out gradually over years and years, creating this persistent, long-term source of contamination that science had just never encountered before. Figuring out this slow-release mechanism was a complete game changer. It meant that predicting the long-term danger and even thinking about how to clean it up required a totally new playbook. So if you've got these particles slowly leaking radiation into the soil, the next massive question is, where does it go from there? How does it get into plants, then into animals, and eventually into us? Well, scientists uncovered this really fascinating process. A major contaminant was radiocesium. When it landed on the soil, sure, some of it was immediately ready to be soaked up by plant roots. But over time, a lot of it got trapped. It would bind super tightly to clay particles in the soil. The best way to think about it is like a sponge that's slowly locking these little particles away in its deepest pores, making them less and less available as time went on. But even with that fixation process, the radiation still found its way up the food chain. And this shows a really crucial point. The biggest risks didn't always come from where you'd expect, like big industrial farms. No, the major pathways were often through natural foods that rural communities depended on, milk from the family cow grazing in the nearby meadow, or wild foods like mushrooms and berries and fish, which are all incredibly good at sucking up and concentrating cesium. So, armed with this new understanding of how radiation actually moves through the world, the next big step was developing practical ways to fight back, to actually break that chain of contamination. And scientists developed this whole toolkit of countermeasures. To deal with the contaminated soil, you could literally just plow it really deep, burying the top layer far away from the plant roots. A more chemical approach was to add things like lime and fertilizers to the soil, which basically made it harder for the plants to absorb the cesium. And for the animals themselves, you could add special binders like Prussian blue to their feed. These would just grab onto the cesium in the animal's gut and stop it from ever getting into its milk or meat. Pretty clever stuff. But the challenge wasn't just about farms. For indigenous communities, like the Sami people up in Scandinavia, their entire culture revolves around herding reindeer. For them, the fallout was an existential threat. Their food, their economy, their entire way of life, all of it was suddenly at risk. And that presents a really, really tricky problem, doesn't it? I mean, you can't just round up thousands of semi-wild reindeer every day for a special snack. So the scientists and the herders, they had to get seriously creative. And the solutions they came up with were just ingenious. They started mixing the cesium binders into salt licks, using the reindeer's own natural behavior to deliver the medicine. Even cooler was the rumen bolus. It's this dense, heavy pill that once a reindeer swallows it, just sits in its stomach for weeks, slowly releasing the binder.
This was a massive leap forward for managing contamination in wild and semi-wild animals.
So these innovations were amazing for protecting animals that humans rely on. But that just opened up a much bigger, much more complicated question. With the humans gone, what was happening to all the other wildlife? This has become one of the most fiercely debated legacies of the whole disaster. The science here is just completely split. On one side, you have studies that have found some pretty serious negative effects: higher rates of cataracts in birds, genetic damage, population crashes in some insects. But then, on the other side, you have different studies, sometimes looking at bigger areas, that have found the exact opposite. They say wildlife is thriving now that humans are gone, and that there's no clear link between radiation levels and the number of wolves or boar or deer. The wild thing is, after more than 30 years, there is still no scientific consensus here. The debate rages on. So what's the ultimate legacy of all this painful, hard-won knowledge? Well, it's that the science that was born in the contaminated fields and forests around Chernobyl has become an absolutely critical part of our global safety toolkit. And we actually saw this get put to the test in a major way. When the Fukushima nuclear accident happened in Japan in 2011, the world wasn't starting from zero. The decades of research from Chernobyl, all that stuff about how radiation moves, which foods are riskiest, how to decontaminate soil and protect animals, all of it proved invaluable in shaping the response and protecting people. And that body of knowledge is still essential today. It informs how we manage nuclear sites, how we plan for emergencies, and how we protect both people and the planet from the unique challenges of living in a nuclear age.
It really leaves us with a tough question to sit with, doesn't it? The scientific advances were huge, there's no denying that, but they came at an almost unimaginable human and environmental cost. It forces you to ask, what is the true price of knowledge when your laboratory is the real world and your experiment is a catastrophe?